It really is quite an honor for me to be here, even virtually in this sort of brave new format that we're pioneering here. And it's also just a really exciting time, like you said, to be doing research in this area. NLP has really changed a lot, and it's been really fun to sort of see it happen. And I'm really excited to share today, both a little bit of a broader picture of what's been going on in the first part of the talk, and then also some details on specific recent projects that I'm also very excited on a little bit later in the talk. So here's a curve. You may have seen something like this before, but it's a little bit cartoonish. So the y-axis is some sort of double log scale or something. Don't look at it too closely. But what's going on here is over time, more and more models are being introduced, and there's this big curve, and they're getting bigger and bigger and bigger. And these are language models, and these language models have just completely revolutionized the way you do NLP. So, if you want to build a modern, performant, high quality NLP system, you're going to start with one of these models. And I'll try to give you some more sort of understanding of the talk today of what all that means, how the scale is really factoring in, how it's really changed things as we've gone through time. But to do that, I want to start out with just a little bit of a review and kind of talk about, what is a language model? How do you build NLP models? Where did this all come from, and where is it going? Okay, so let's take, a time warp back to 2018, which, feels, if you're a young grad student in the field, this is kind of like a phase transition. You don't even read papers before this anymore sometimes, because everything changed so much. But before 2018, there's a lot of great work in building neural models. They had already taken over the field. And the way you would think about solving a problem is you would go and gather as much labeled training data usually as you could. You would perhaps do some pre-training of some word embeddings. So maybe you would have some vectors for each word that were trained on a large corpus, but mostly you would just have labeled supervised data, and then you design a custom neural net architecture for your problem. And this is a particular architecture done from some of my colleagues at the University of Washington. That was really beautiful architecture. It was for a question answering problem called reading comprehension. You don't need to understand the details of this, but just think about, this was really nicely designed for this task, has some really custom attention mechanisms, worked really well for the task. And that was kind of the game you played, is for every problem you had a custom approach, you got as much data as you could, and you trained it all supervised. Over the last 3 years, what's happened is that the story is completely different. So no longer would you make, no longer do you need so much labeled data, no longer would you make a custom architecture. Now you're going to start from a language model. That language model is going to be pre-trained, which means that there's a large amount of plain text that's used to estimate the parameters of that model. And then it may still be fine-tuned, trained a bit more on some labeled data, but it's a completely different paradigm, a completely different way of going about building models. Okay, so to try to take you through this piece by piece, let's just start at the very basics. So what is a language model? In the simplest form, the language model is just a distribution over strings. So it's a probability distribution. You can estimate it from some text. Most language models break the probability of a string into the probability of the individual words in that string, where each word can be generated conditioned on some other set of words. So I'm showing some particular order of conditioning here. You could do it some other way. Throughout the talk, I'll defer to different things that are sort of variations on language models that make different assumptions about how to do this decomposition. But fundamentally, you get a probability for every word, and you multiply those probabilities together to get the probability of the string. Now, this seems nice and fundamental, but maybe not so clear how that's going to hook up to those more complex architectures I was just showing you. So before 2018, of course, there was a rich literature on doing language modeling, but roughly speaking, they were used in places where you did text generation. So think about machine translation or speech recognition, where you needed to actually produce strings in the output. And they weren't really super used broadly in all kinds of other things like classification problems or question answering problems or things like that, where they're really going to take over. But actually the framework was there. And it's actually, when you think about the revolution that happened, it's even a little surprising it didn't happen earlier. I mean, I know there's good reasons, and you can think about this yourself, but the ideas and the framework were actually laid even 10 years ago in this very seminal NLP from scratch paper from Colliver and Weston and others. And they said, following our NLP from scratch philosophy, we have dramatically, we're going to make use of unlabeled data. We're going to train the model this way. And they even trained their word embeddings from language models in these papers. They didn't do it the way that caught on and took off later with all these other methods we know so well. But the caveat here was that, very long training times, are going to be a problem. And, if we had more compute, we'd use more data and things would get better. So they kind of already knew this, but the field largely ignored it. And it's kind of interesting in hindsight to think about, why didn't we figure it out sooner? And then particularly being involved in the Elmo project, which kind of started the trend, I wonder why we didn't see it sooner. Okay, but then post 2018, now it's everywhere. You can do everything with it. And let's try to understand that a little better. But before we do, why is language modeling even, a reasonable thing to think about in NLP more generally? So, you could think of the notion of AI completeness, right? So if you solve this problem, you would solve all of AI. Well, I don't think that's true for language modeling. Having a really good language model or distribution over strings is not going to solve vision or robotics or, planning or all these other really rich problems we care about in the AAAI community. But, what about for NLP? Could it be NLP complete in the sense of, any NLP task you could define on text only? Yeah, I think, probably not. But there is actually a lot of signal there. So let's look at some examples. So there is world knowledge just in what strings you're likely to see. So, they ate pizza with pepperoni or chopsticks. One of these is going to be much more likely. Whether you can get a deep understanding of the causality there and the geometry, unlikely, but you can learn some interesting correlations. Things like co-reference, John, Rob, Bill, he was arrested, terrified, bored. You're not going to solve these classic Winograd schema challenges necessarily. You won't be able to distinguish this perfectly, but there will be a lot of signal for things that shouldn't appear. And that gives some indirect signal for what's going on with the co-ref. And even there's rich multilingual signal. This is kind of a silly example, but there's multiple languages. There's kind of definitions of things. There's all kinds of interesting signal for understanding what's going on. Okay, so that's kind of the intro and the background. And what I'm going to do now in the talk is two different parts. So the first part, I'm going to go on this trend. I can't cover all of these models. There's a lot of beautiful innovations going on here, but I'm going to pick a little path through here to give you some of the higher profile models, some of them things you may have seen, like most recently GPT-3 and other models like that. And I'll try to tell the story. So the story you might often hear is all about scale. So, what's going on here is it's just more compute and more data, and that's the reason there's gains. And that is absolutely a factor, and there's no question that that's transformative. But I would argue there's a lot more creative things going on, and there's some really clever formulations and some really nice steps, and I'll try to highlight those and point them out as we go, how much of it is coming from compute and how much of it is coming from very clever formulations that, of course, also enable compute. And that's part one of the talk, is really about scale and understanding some of these models and what they can do. In the second part of the talk, I'm going to just focus a little more on my own work and some projects led by Mike Lewis and FAIR Seattle, and talk about actually understanding a little bit more, like not just pushing scale, but trying to understand really what works and why it works, and trying to generalize these models so they can do ever more tasks and we get sort of more and more general purpose techniques. And that's kind of something we've been pushing at sort of, you could call this large, but not on the exponential trend scale. Okay, and we'll come back and talk about that in the second half. Of course, in this graph here, the y-axis is the number of model parameters. And I think that is, a good proxy for what's going on. But actually, if you look at the GPT-3 paper, they visualize this a little differently in this nice graph that I stole from them. And here, the y-axis is not number of parameters, it's actually the amount of compute spend. So the amount of flops and some measurement of flops and how many sort of GPU years are sunk into the model. And I actually think that's the better predictor. And so we'll try to talk about that occasionally when we go through the models too. And then the other thing you see here in these different bands of colors is that there's actually fundamentally different classes of models. So there's sort of classic language models, there's mass language models, there's so-called seek-to-seek models, and these are these different colors. And I want to kind of walk you through that and try to help you understand what the different models are and what they do. And but the overall predominant trend, no matter what model class you're in, is one of this computational scale. Okay. Right. So take a deep breath. Here's the set of models that I want to go through in this first half of the talk. I'm going to do this at a somewhat breakneck speed. I would love some hard questions about them at the end or things I might have skipped over. One really fun trend is to see sort of not only has all this work been going on, but it's actually been getting quite a lot of recognition along the way. And of course, there's lots of other related papers that I can't possibly all cite, but in particular, some early ones that were on the trend that don't always get recognized that I think it's worth looking at, but I'll stick to this particular pattern. And what I'll try to do is show you the key idea or two, just a few slides that takes us through the main ideas without going through all the possible details. Okay, and I was very happy to be involved with the ELMO project. This was at the Allen Institute for Artificial Intelligence at the University of Washington before I moved to Facebook. And then these other projects are by teams at other wonderful places. So the key idea that got all this starting, and this is really the driving factor and what we, I think, did a good job of pitching in the ELMO project, was that, like if you think back to that first slide where I showed you that big neural architecture and we just had these single vectors, one for each word that were pre-trained, you don't want to have just a single vector for each word. That's not going to give you an expressive enough model. So for example, here, if you think about the word play in these two different contexts, if you're going to turn that word into a vector and feed it into a neural network, it's sort of intuitive to think that the vector you would want for that word would be different in these two different contexts. And that in general, we should be thinking about word meaning in a rich, sort of contextualized way. Okay. Now, when we were working on this project, luckily, the question became, how are you going to get those vectors? How are you going to understand those words in context? And luckily for us, there was a really beautiful literature and some really great methods for computing, sort of vectors of words in context, and it was based on neural language models. So what I'm showing you here is a language model. It's got some layers. It's got a particular nonlinearity. It was an LSTM back then. This will change to transformer soon. And it will go left to right through the text. And it will compute multiple layers of vectors. That's what these little boxes are. These are real vectors in R to the n. And then at the end, this final vector will be used to predict the next word. So this will range over the whole vocabulary. And you'll have this kind of projection onto the vocabulary to predict what word's going to come next, and that will be the loss that drives the training and so forth. And so when you think about these mechanisms, they're really well studied, they work well, you get good models. One way of thinking about them is they're a function that maps a part of a sentence to a single vector that best summarizes it, that best allows you to predict what's going to happen next. So it's almost trying to learn like a sufficient statistic or something that clusters all the possible left side prefixes and gives you a good representation for what's going on in this context. So we already have that mechanism, but now the trick is we want to actually not just look at the left of the word, we want to look at both sides of the word. So we need to have some representation also of what's going on the right-hand side of the sentence. But for the ELMO approach, we said, well, let's just run a language model in the other direction and train that model. We'll have these two separate models. They're both easy to train. They're just predicting words, predicting them from different directions. And in the end, when we get some contextualized representation for this word, what that representation will be is some function of a whole bunch of vectors that can appear around the word when you run the models in both directions. And we had some fun playing around with this function, and we came up with a particular one you can look in the paper. But the key idea is just that these representations that you trained as a language model can be extracted out, and they can be put into another model that's then going to be tuned from some supervised data, and give you the right answer. Okay, now it'll give you a good model. And now the tricky thing was the ELMO mindset is we hadn't yet made the transition to where we're going next. We were still thinking about these custom architectures. So we were thinking about this as a replacement for word embeddings, and you're still going to have your QA specific model or your co-reference specific model, or whichever model you care about, and these are going to be fed in at the bottom, and the whole thing will be trained. Okay, so that's how we did it. And here are some results. This was kind of the state of the art for a bunch of really hard problems on the left for each one. Our model, where we tried to replicate that, is actually kind of hard to replicate state of the art. This is one of the problems with having custom architectures like that. And then on top of our replication, we put in these ELMO embeddings, just a simple swap out, and got these sort of really, really nice gains. I mean, it was kind of I think one of the main contributions to the ELMO paper was just very careful evaluation to show how well this whole approach works. And it really kind of convinced the community that this is something that we need to really focus more efforts on, because there's going to be huge gains to be had here. Okay. And, this is simple, general, built on some ideas that were recently around, really proved this was a good direction. But we were still assuming these tasks, custom architectures, that we now know in hindsight was definitely not the way to go. Okay, so what's next? It's going to be the GPT model, and I think there are many nice things about this model, GPT-1. But the question that I really like to ask them, that I think they did the best job on, is why have those word embeddings? Why have those custom architectures at all? We can do better than that, and I think they showed it very convincingly. So they're going to switch to a different kind of language model. So this is a transformer as opposed to LSTM. I don't want to teach you the details, but in the previous picture, there was a much sparser connectivity, and the transformers can look much more densely, and they can train on much longer text, and that turns out to be advantageous. But that's kind of a different talk to get into all the details of architectures and so forth. But they sort of training this transformer language model. And they're just going to train it as a language model. So this kind of predicting next word loss is going to backprop all the way into this network and give you some cool representations. And now a really interesting insight that goes beyond just scaling was this idea that actually now what if we can just kind of turn everything into a language modeling problem? Okay, so what does that really mean exactly? Well, let's say you want to build a classifier, so something that would, for example, classify text according to its sentiment. Well, I can mark the beginning and the end of the sentence or something, have some special tokens in the input, and I can just feed that into that language model we saw from the last slide and get a vector out. Maybe that vector will give me a good representation that I can do some sentiment on top of. Of course, we don't always want to just classify a single sentence. What if you want to compute textual entailment? So textual entailment is a problem that takes two sentences as input. And you ask yourself, does one sentence necessarily imply the other? So, custom models for this task would, separate those two sentences and do lots of really cool stuff with them. But, what OpenAI folks said was, let's just feed this all in, just concatenate it, make it a string, feed it into this block of transformers, get some representations out at the top and see what we can do with that. And I think this is really very clever and very transformative, the way of thinking about things. It will be picked up again in lots of other approaches. So, you can do text classification by just putting a little linear layer on top of your transformer. Entailment, you just put the two sentences together. Similarity, you can do other things. Maybe you do a few encoders, maybe you don't. In the later GPT models, this will even get simplified and streamlined even further. But the basic idea is that these models, you only need very little changes them to make them to do lots of different tasks. In each case, you can fine tune. This will go away later, but it's still fine tuning at this point. And you can get some really good models for doing things. Okay, so here's some numbers from the paper. I have to admit, the set of tasks changed, and in hindsight, I kind of missed a trend here. I wasn't totally sold on this uniform architecture. I was convinced that custom architectures are still going to win. Nobody's perfect. In hindsight, I was very, very wrong. And there wasn't the same set of tasks as we used in the Elmo paper. But it's pretty clear that they had it right and they were on the right direction. And it's totally won out in the long term. So you got this longer text, you got this self-attention. The idea of this unified architecture, this is NLP now. Like, you can still do a little customization, but you're always going to start from these unified blocks, and they're going to get you tons of mileage. And usually that's all you need. One cool thing about this training as this left to right language model is that it's going to scale up really nicely. And so there's GPT-2 and 3, and I'm sure there's newer versions in the work at OpenAI that I don't have any insight into. It's the scale thing is just really, really impressive there. But a caveat and something that remained open is that it's not bidirectional. So in Elmo, we were really motivated by that bidirectional 2 model thing. And here we're saying it's strictly left to right, which we'll come back to a lot more throughout the talk and talk a lot more. Okay, so, but of course, along comes Bart. And Bart says, well, we can do what OpenAI is doing, but we can actually have a really interesting way of making it bidirectional. And of course, there's lots of other things going on too, but just to kind of simplify it down to a clear delta. So this is the so-called masked language model. So what you see here is basically the same block of computation you saw for GPT. But now these transformers are not only going to be going left to right through the string, they're going to be attending to everything. Of course, how do you predict a word if you already saw in the input? That's not going to work. That's why that left to right thing was so nice. It allowed you to predict the next word. And the masked language model, what you're going to do is just remove the word. You're going to take whatever word it was, you're going to mask it out, and you're going to encode everything else and repredict it. And that's going to allow you to have basically the exact same loss, the exact same signal you have for any other language model. Okay. And they built on top of the idea of this unified architecture, and they said, yeah, we can do it, but now we can do all kinds of other things like tagging tasks, where you're doing things on the individual tokens. The sky's the limit. We have a much, much broader range of tasks. I would say it's still hard to generate text from this model. That's one drawback, But any sort of classification style task, very broadly construed, not just sort of binary text classification, is going to be fair game, the token and span level and so forth. It's going to work really well. And then, of course, the results speak for themselves. I don't have to go through this. Everybody knows this, but just blow away numbers compared to what you had before, and a really nice, careful comparison. A really, really good job of convincing people. I think at this point, we're all off to the races. Like, this is the future. It's a really big deal. Completely changed the field. And of course, comparing back to that original slide, these custom architectures are just gone now, and they're probably not coming back. But we'll see. Who knows? I shouldn't make predictions like that. Okay. Bidirectional reasoning is important for many tasks. We'll come back to this more throughout the talk, but it's crucial for lots of the time. And in those cases, you're going to be a lot better off with a model like this than a left-to-right model. Although, as things scale, maybe that trend will change, but at a fixed modest model size, that's definitely true. And it's the focus of really intense study. I'll highlight just a few things following on to Bart, including one slide on the Roberta model, which we did at Facebook. And it was really just, you can think of this as like a replication study, where we actually kept the model size fixed and asked the question, what if you tuned this thing even better and just threw more compute and more data at it, but otherwise didn't really change much. We actually simplified it and streamlined it as opposed to making it more complicated. And one interesting fact that is kind of worth realizing is that the original BERT results, it was this giant gap, giant gain. This left two bars here. But that if you actually throw even more compute at it, even without adding more parameters, you just keep getting more and more and more gains. And so the original architecture and the original approach really was probably about twice as good as it appeared in the original paper. And so if you want to use one of these models, it's probably even better than Roberta now, but it's definitely like a very solid option, probably about as good as anything else still for the mass language model case at this model size. Okay. And then PostBird, things have just gone completely crazy. We're living in a totally new world. BERT is like, at least softly inventing things that looks a little bit like linguistics. It's, learning significant world knowledge. It enables really interesting cross-lingual and multilingual learning, which you could do a whole talk on. But, I can't help but mention it. This might be one of the next big things in NLP, is that we actually are building models that jointly work with lots of languages all at once, not just English. And there's a whole different subfield. And if you're interested, I'd really point you to this really nice paper on the primer of Bertology, which just is a beautiful, very recent survey of this field. It's hard to keep on top of it, but they've done a really good job. Okay, so now let's move on a little bit from BERT and say there's lots of other really great things going on when we're moving up this scale axis. One model out of Google is the so-called T5 model. And here, one way of thinking about this model, there's lots of ways of thinking about it. And we, in the second half of the talk, I'll come back and talk about BART, which is sort of a simultaneous discovery. We sort of invented a very similar model at the same time. But T5 did a really good job of scaling. And they also did a really good job of kind of thinking about architectures that kind of blend the best of both worlds. So if you think about this, they have a bidirectional component that's going to input some math thing. And then they're going to do what's a common trick in machine translation. You're going to encode a string and then use this left to right model that you can actually sample from to decode another string conditioned on it. So you're going to mask out certain spans, and then you're going to have a decoder that recreates what text was missing from the other one. So you can think of this like a machine translation problem. Given a string missing some information, generate that information again. Okay. And it builds on all the machinery that was developed for neural machine translation, which would normally translate between languages. And then they had this really very nice idea that now, once you've got this very general machinery, you can sort of think of every possible problem as just mapping from strings to strings. So, you can do multitask learning, both at the pre-training time and also the fine-tuning time, and think about all these different tasks as just a very, very general function from string to strings. And that seems to work, really well. It's a really nice way of thinking about it. And importantly, you get sort of whole new ranges of tasks you can do here, things like generating text and so forth that the previous models just couldn't do at all. And they also took it to a larger scale, which is really nice to see that effect. Really, really great experiments. I won't try to cover the paper in any detail, but really great exploration of all the different ways of combining things and multitasking things and combining pre-training and fine-tuning. and really, really great explorations of scale, which is something that we sort of stopped doing at some point. And I'll talk about that in the second half of the talk. But I think they did a really great job and really scaled this up nicely. And they've got some cool models that you can use now. Okay. But back to the most recent model. Now, I think I just go back, and retouch on GPT-3. And actually, this is kind of a little bit of a hybrid of the GPT-2 and 3 story kind of mixed together. But they're continuing to push on this scale, and there's sort of a real beauty to what they're doing. But they're sticking with this left to right model, which is an interesting choice. It has, has lots of benefits. It scales really well, and they're also coming up with really clever ideas about how to actually use these models. So they're saying, well, actually, you could just do zero-shot evaluation. So you just really think of everything as a language model. So if I want to do QA, I put Q colon, I put the question as a string, A colon, and then I have the model continue generating a string, just based on the distribution of our strings it's learned. Or similarly, if I want to do summarization, I think of some other way of priming it. These are actually a little bit older patterns from GPT-2. There's newer patterns in GPT-3. But there's sort of the idea is that everything really gets even more so reduced to a language modeling problem of just predicting or completing a string. And you actually get some very interesting results and surprising leverage by doing this. Okay, here's just from the GPT-2 paper, some cool examples of the kinds of things you can do in question answering with that. These models learn, T5 also showed this, these models learn a surprising amount of world knowledge about facts and things like that. And then really nice exploration of scale. So this is a figure from the GPT-3 paper looking at zero-shot, one-shot, and few-shot learning. So you can actually add information to these models by giving them training examples encoded in the string, and then asking it, given that you've seen all this string with all these examples, how do you complete the string? And the more and more information you give it, of course, it helps, but the really predominant factor, more than the amount of supervision you're giving it, is the scale of the pre-trained model. The bigger and bigger the model gets, the better and better it does in these kind of few-shot settings, which is really amazing. And then finally, just really, really good at generating text. So, of course, I think everybody probably saw these demos and so forth. So I hope you have a little bit more insight into what's going on now if you haven't read the papers carefully. And, just really, really beautiful results. Okay. So overall, one of the largest dense models to date, I don't have any slides on it, but a trend going forward is going to be sort of more conditional compute, more efficient compute, because, the amount of compute that goes into training these models is really, really a lot. But the few-shot performance is a huge deal. Really interesting to see where that goes, although I don't think it's quite yet rivaling what you can get with fine-tuning of smaller models. We'll see how that plays out in the longer term, and just really interesting approach overall. Okay, so of course, those aren't the only models. There are many, many other ones. I can't possibly do it, but think about, all these, there's sort of at least 2 or 3 clever ideas in every one of these. It's not just applying scale. It's really lots of twists and turns of how these models are set up and so forth. And so, I could go on for hours, but that's your sort of intro to the field and thoughts about the trends that are going on. One caveat, this is a new slide that I don't always have in this deck, and I think there are drawbacks and limitations to this large-scale language modeling, and that it's important that we acknowledge them. We're getting these amazing numbers in the benchmarks, but of course, then we realize the benchmarks aren't actually as hard as we initially thought. We know this isn't really going to get us all the way to human-level language understanding, and we should understand better where we are. High resources required, high carbon footprints, the data itself, is sort of very, very data hungry, and you start just kind of ingesting all the data you can get your hands on. That could be a problematic trend too. And there's a really nice recent paper, which I'm sure many of you have heard about, cited at the bottom here, on the dangerous stochastic parrots, which I'd encourage you to go read along with a lot of the other citations. And, I think these issues we're going to have to grapple with these as a field. And, I don't have an answer yet, but I think that it's important that we at least talk about it and mention it and acknowledge it. Okay, so that's the first half of the talk. And what I'd like to do now is kind of go off on a different tangent and, talk about, our efforts a little bit more self-serving and trying to understand, how do we generalize those early models? This is kind of a little bit of a branch point right around when T5 happened, is when we went off and started doing these models a little bit before that. So how do we support more tasks? And we were specifically thinking about text generation style tasks at the time, but how far can we push this? And in general, these different ways of doing the self-supervision, language model, the mass language model, the seek-to-seek approaches, which are based on MT, like T5, based on machine translation, what's best and how do they compare to each other and how do we actually compare it? Because there's so much changing in all these different systems. And that motivated us to slow down a little bit and try to see what's going on and develop some models that could do some careful comparisons and understanding. So I want to start out by talking about our Bart model. And Mike Lewis was the real driver. I should have his name on the slide. I apologize to Mike, but he's really the driver. And there's a large team. I have the names on the slides at the end. A large team of folks involved in doing all these projects. And our motivation was not unlike T5 in that we knew that there were good bidirectional models. Okay. And those would be good for things like classification and question answering and things like that. And we know that there are good left to right models like GPT and so forth. And those are going to be really good at doing generation. And so, can you do the best of both worlds? Can you get a single model that does them both? And more generally, how do we understand the trade-offs and how do we measure more carefully what's actually going on with these different models and how they compare to each other? So Mike came up with this really beautiful Bart model. And it's sort of the idea here is that it's really simple and very general. So the idea is that we're going to take this so-called sequence-to-sequence model. This is literally off-the-shelf machinery for doing neural machine translation. But instead of mapping, say, French to English, we're going to take the English sentence, we're going to noise it, we're going to modify it somehow, and then we're going to learn a model to map that noisy English back to the original English. Okay, so I'm showing an example here where I've knocked out some tokens. So this would be the equivalent of the masking that was going on in both BERT and T5. Okay. But the cool thing, and this is a slightly more general formulation than T5 explored, was that really actually this mechanism allows arbitrary noising because we want to reconstruct the whole string, not just the information that was masked out. Because we're reconstructing the whole string, we can actually allow for arbitrary noise functions. So you can do any kind of noising or perturbation to the string you want. You can train a Bart model based on that, and you can see how well it works. And you can try to do a more systematic comparison between the different options. Okay, and that was a big part of our motivation. Just a few examples of some of the noising stuff we looked at, just to give you some little bit more deep dive on this project. So you can, of course, mask tokens, like we talked about earlier. You can actually delete tokens. So you don't even have to give the model any indication of where the information was that was missing. Another trend that was happening as the transformers got better and the models got higher capacity is that we've been moving to longer and longer chunks of text as a community. And so, you can think of the inputs to these models now as documents. They're more like 512 tokens or something, not super long documents, maybe sort of 2-3 paragraphs. But that allows you to also think of sort of clever strategies of noising around documents. So you could rotate the sentences around the edge of the document and have the model unscramble what order they came in. Maybe that gives you more high-level discourse kinds of cues about what's going on in the text. You could also, for example, permute the sentences in the document and have the model go in and try to recreate the original order of the sentences. Maybe that gives you some interesting information. And then finally, you could do something which, spoiler alert, this is going to work the best, even though, it's not quite as different as we were hoping for as we were doing this exploration of all the possibilities. We can do what we call text infilling. So in text infilling, you can take longer spans of text, not just a single word, replace them with a single mask token, and including zero length, so sometimes nothing at all, and ask the model to recreate the original sentence, giving this particular type of noise. And so you can think of this as a generalization of a mass language model just to spans, which can be zero length. And it's built on SpanBERT and other models that kind of showed that was the right direction to go. We did a real systematic comparison here. One caveat of doing these systematic comparisons, like I've been trying to motivate, is that, of course, it's compute, right? So, we can't, take, a gigantic model and do all the different variations of it over and over again. The field just, that's not possible. So it's an interesting space to be working in because you can only train so many big models. But we did this at a slightly smaller scale, the scale of the so-called BERT base, which is still a pretty big model, but it's smaller than the ones that you're seeing now. And we did our best job of re-implementing kind of various models that existed then. And I'll really refer you to the paper for all the details of what's going on. But in general, what we're finding here is that masking and deletion type of losses or noising functions are really important for more classification style tasks, and in particular for like question answering where you need to pick out a span of text. Having that bidirectional signal and that masking is really, really important. Not too surprising given what we know in hindsight, but it was really nice to measure that, more systematically compare it. And of course, on the flip side, and here this is a score where lower is better, if you need to generate text for something like summarization or just kind of free-form text generation, you really need that left or right component in the model somewhere. And so you really need some part of the model actually generating full strings. And so, things like the infilling and so forth are going to work much better there. And previous models that do that, like GPT and other pre-training approaches like maths, are going to shine in this setting. And one nice thing about the Bart approach is that we get the best of both worlds, so we're able to do well across all the different settings. Okay, so we also scaled up a bit. I'll run through some results here for our this is that little data point I showed you on the graph earlier. This is not going to be gigantic compared to the other models that are going all the time, but it's not a small model either. If we compare it to Roberta on classification, which is this kind of better trained version of BERT that we did, we're able to do as well, sort of matching some strong state-of-the-art types of numbers on various tasks that I won't take you through the details of those tasks, but it's doing quite well, which is nice because we had a lot of extra mechanism and we didn't fall behind. And then places where a model like this is going to shine are things like summarization. In particular, this summarization task is a very abstractive summarization task. So you need to actually, synthesize. You can't just copy and paste strings from the input to make a good summary. You need to actually synthesize new strings that you haven't seen before, or at least put the words together in novel ways. And that's where we're going to see bigger gains over previous methods, including like a BERT model that was adapted specifically for abstractive summarization. We get some very nice gains there. Just to give you a feel for how this model works, it really, this is kind of where Bart shines. It sort of makes sense. It's kind of reconstructing text. It knows how to piece things together. Here's an example summary that went quite well. So what we see here is that there's a particular diplomat and there's some incident going on. I'll give you a second to kind of read over the text. And there's a bit of a dispute. Is this diplomat going to be deported? And you get this really nice summary out when you run. This is Bart that's been fine-tuned for summarization on the summarization data set, but pre-trained in the way I said. So Boris Johnson has said that he will raise the issue of U.S. diplomatic immunity with the White House and quizzes with the White House. So some cool things that are going on here is, information is getting pieced together from all over the input document to come up and figure out sort of who's doing what and what's actually happening. This is both kind of at the entity level and also at the event level, kind of piecing together what happened and getting all the arguments correctly together. It's really beautiful. There's some nice encyclopedic knowledge. It's even a little bit subtle. You might not catch it at first, but the first name of the diplomat here is not actually mentioned in the text, but of course, somewhere in that pre-training corpus it probably was, or maybe it's lucky coincidence, but probably it was in the pre-training corpus somewhere and the model's able to bring it over. And one tricky thing here is that the model can make some pretty subtle mistakes. So, you may not have catch this. It takes a careful reading and a keen eye, but actually, Anne here is not the diplomat, it's the wife of the diplomat. But it's a beautiful text. It reads beautifully, and it's actually factually wrong. So that's something to keep an eye on with these kinds of models, is that they do make mistakes, they do kind of hallucinate, and there's open work to do in this space. Okay, so that's kind of our overview of Bart. I want to just briefly mention one other trend that's going on that's really fun. We didn't start this trend. It started with cross-lingual language models on top of BERT and other things. But there's this thing that you can do with these models, which is just really shocking, and that's the multilingual learning. So what you do is you take your corpus of English and you've got your noising function, whatever it is, and you get some other corpus of text that's just in some other language, any language you want. Get another corpus, get another corpus. It's all just plain text in all these different languages. And you just concatenate all this text together as if it was all just one big data set. The model does have language ID, so it does know kind of which language it's working with. But otherwise, it's a shared, vocabulary and everything, and it's just going to train this one big model, pre-trained on all these data sets. And then once you've done this pre-training, you can fine tune it for machine translation and lots of different language pairs. And what you find is that it just makes a much better machine translation model. In particular, one caveat here is I have cherry-picked these languages pairs a little bit. So I'm showing you here language pairs that are not super high resource, like German, English. There's tons of data for doing translation, and you would not expect to see a gain in a case where you have a lot of labeled data to tune the model. You wouldn't need the pre-training, but in even medium to low resource settings, you get some really nice gains. And then one cool thing, which I'm just going to have to go through very quickly, but I want to give you a flavor of, is that what's really going on is that even though those were just a bunch of concatenated monolingual corpora, somehow internal to the model, it's learned to align things across the different languages and share across the different languages. So one thing we can do is, given data in a language pair X to English, where X is some language, you can see the different options here on the graph. We're going to fine tune on that data, teach it how to translate from X to English, and then test it on Y to English, having never seen any examples of input-output pairs from language Y to English. Okay, and because X and Y were both in the pre-training corpus, and because it somehow aligned that information, you get non-trivial transfer. I mean, this is not going to be like a super high-quality machine translation system, but you get non-trivial transfer, especially better in closely related language families. And the model has actually learned to do some pretty interesting things. These are blue scores, so but higher is better. And some of them are not embarrassing, but overall, I wouldn't say they're the very best scores you could get. Okay, so for the first project that I wanted to show you, this Bart project, we're really thinking about this arbitrary noising. We're really trying to do more careful comparison, thinking about generation and classification. And of course, we have this fun exploration in a multilingual setting. And that's a completely separate MBART paper, which I encourage you to look at. And this is sort of very nice results there. Okay. So for the last project, with my remaining time, what I want to do is show you our most recent model that's come out. This was led by Mike Lewis again. And here the question is, okay, we've now got a pretty good understanding, especially from doing Bart and other models, of all the different kinds of ways of doing variations on denoising autoencoders or mass language models. Can we find any new sources of supervision for doing pre-training, any new directions of things that are, eventually can give us another game changer? And we'll see. I mean, we're not there yet, but we're exploring possibilities. And we've got one candidate, which is the so-called Marge model that I'm going to tell you about now. And we'll see longer term how it actually plays out. So in Marge, the key idea here is that you want to try to learn to paraphrase. So the paraphrasing problem is to sort of take a text and rewrite it sort of syntactically or superficially different so that it has the same semantics, but it's actually a very different text. And the idea is that in that kind of a setting, there's a lot of information for learning about language because you learn all the different sort of reasonable transformations of a text. And the idea behind Marge was that actually, if you have a large plain text corpus, it will actually be multilingual. But for now, just think about English. There's going to be lots of variations on some text in there, and maybe we can sort of simultaneously go out and retrieve or discover these paraphrases. And at the same time we discover the paraphrases, we can also learn to transform them back and forth to each other and get a really strong signal for doing unsupervised pre-training. Okay. So the overall approach is going to have these two stages of retrieval, which is discovering documents that we think are paraphrases of each other, and then reconstruction. So learning how to map between the different documents and explain how they paraphrase each other. So let's talk about those in just a little bit more detail on both of those. So the goal of the retrieval step is to find documents that have the same information, but that's might be too tall of an order to get an exact paraphrase, an exact reordering. So what we're going to instead do is say we're going to find a set of documents, and in aggregate, we'd like that set of documents to have roughly the same enough information to recreate the original document that we were driven by to do this retrieval. So here's one example in English that has some of the information. Maybe you get another example that has different facts, some of them overlapping, totally great. It turns out for this approach, we started out multilingual rather than adding it on the end. And so maybe you get a document in another language that also has some of the information. It could be completely different scripts, so forth and so on. It's all great. And the goal of retrieval is just to get this set of documents that will then drive our paraphrase-driven learning. It turns out this is all going to be integrated into one big learning system. I'll point you to the paper for all the details. But basically, documents get embedded into a vector. You do nearest neighbor of that vector space. If you train that embedding right, you get things that actually are paraphrases in the way that we want. There's a little bit of some tricks here to make it work. So we tend to actually only retrieve documents. We restrict the documents to only be published on the same day. And so one way to think about this is like you're getting lots of people describing different versions of the same news event or something like that, and you're getting a rich signal of paraphrase from that. But with that caveat and that restriction, actually you can get this whole thing to start training from a random initialization. So you can just think of that as like randomly hashing the words and having the date constraints and actually getting enough of a signal to actually start the whole training process. Okay, so given that you have these documents, what you need to do now is learn to reconstruct the original, and this is this paraphrasing step. And here we're going to actually just use the same machinery that we saw before for T5 and for Bart and for these other models. You can just think of this as a machine translation problem essentially, but it has multiple sources. And that's okay. That's actually a version that's been studied before too. And you can do that. You can run part of the part of the model that's bidirectional on all the different documents, the part of the model that's left to right only on this one you're reconstructing, and combine the information, and it works out fine. You can look at the paper for details. And there's some cute tricks, including like using the retrieval score to reweight the reconstruction score that actually allows you to get a joint model. But I won't go into those details here. Yeah. Okay, so to summarize this approach, what's going on is that we now have a single unsupervised training objective that in many ways combines a whole bunch of different tasks that we care about. So there's an aspect of multi-document summarization going on here. There's an aspect of machine translation. There's an aspect of information retrieval, and an aspect of paraphrase, and somehow it's all kind of munged together into this one task. But the beautiful thing is that actually now it becomes closer to end tasks we care about. So if you can, if you just control the model, so for example, force it to go between different languages instead of giving it the whole set, and that turns out to actually be true. So I won't take you through all of the details of this model, but I will show you some so-called zero-shot results where we just restrict the model to actually do one of these different things and see how well it does without any further fine-tuning or any further training. Okay, and it actually gets some pretty reasonable results. By no means have we solved any of these problems. So here's an example where you're doing by-text mining. So you get a sentence in one language in a large, but the original sentence would be in English, and these are the other languages. And then you need to just retrieve a sentence that has the same meaning. So this would be making by-text or finding cross-lingual paraphrase. There's another way of thinking about it. This task would do much better, but this is a high-performing system that's working very well, considering that it's unsupervised. Another cool thing you can do is just document-level machine translation. So we're just going to give you a document entirely in one language and then ask you to output something in another language. Model knows how to do that because it gets language ID at training time. And here you get non-trivial results. So these are blue scores. I'll show you some examples in a second. Translating into English is a lot easier for the model than translating out of English, which is interesting and kind of makes sense given some stuff I'll show you later in terms of the data stats and how everything worked out. But you're getting sort of non-trivial machine translation, having never had any signal other than this automatic bootstrapping for the paraphrase retrieval. Well, I'm not showing you the source text here. The source text was in German, and now you're going to English. So this is like one of our best language pairs. And I'm showing you the reference English along with the output of this zero-shot unsupervised translation model. Okay, and give you a second just to look at it. It's by no means a perfect translation, perfect output, but it is, I think, very nice considering what the model had to learn from, and in general, a reasonable job. Here's the same example translated from Arabic, and I would say that the performance degraded. And here's the same example translated from Chinese. Okay, and here it's even harder. So the paper has all kinds of analysis, and I encourage you to go and dig into it if you're interested. But I think that this is probably a pretty good place to stop and give you a feel for kind of what's been going on. So to summarize the March part of the project, we're really excited about a lot of aspects of it. One is we have effective pre-training without mass language modeling or causal language modeling. It seems to be a fit. but hopefully it will scale up well, and hopefully things will work quite well. And this general theme of kind of thinking about the relationship between together, so that the fine-tuning, the pre-training someday all merges into one, and you get more zero shot. We find that really exciting. The whole theme of the second half of the talk was on denoising sequence-to-sequence pre-training, sequence-to-sequences as empty techniques. And we sort of have all this sort of coherent theme, and we're trying to keep pushing this and see how far we can take it. Special thanks to everyone that was driving those projects. These are big engineering projects that we did, and they're not easy. And Yen-Han and Mike and others really deserve a lot of credit for leading those projects, and everyone is contributing quite a lot. So this is kind of the visual summary of the two parts of the talk, both on the scaling trend and on the sort of more, still large but more modest, and trying to understand the signal trend. And with that point, I will leave you a summarization. Maybe that's a good thing to leave up. I can post some more questions. Happy to take questions.
Thank you, Luke, for a very interesting talk, and also giving us a summary of the field as it is evolving, and the questions that they are posing. So I am a little curious about the way you started. You said that would these language models give us important insights in AI, and you weren't very sure about it, but definitely they do give a lot of insights in NLP. So maybe it's the time to go back to that question and ask ourselves, what have we learned that we can use for general AI problems? Do you think we haven't learned anything, or do you think that there are aspects of this that would be really, really valuable for the broad AI, very different problems that we study in AI community?
Yeah, well, I think that maybe I was being a little bit unfair. So I think there's some beautiful sequence modeling going on here, right? And there's lots and lots of AI that can be thought of as sequence modeling. So in that sense, it's a very general technique that I'm sure is going to pay off in related areas, vision, comp-IO, and other areas. In terms of things like embodied robotics or something, I think that's maybe a bit more of a stretch. But there's going to be some beautiful marriage of these ideas at some point. Just because the one mechanism doesn't solve everything, I don't think that's a bad thing. And we'll figure out how to get this language stuff to work better, and we'll figure out how to ground it. Maybe that'll be an extra mechanism. I don't know. Maybe the grounding will be somehow reduced to a stream of tokens that we can model this way. Already it's happening recently in computer vision that you're able to do more of this and get models that look like this to jointly do text and images, which is pretty amazing. So, maybe this is another example where I'm wrong and the field's going to prove me wrong, and I'd be really happy to see it if true. But that's kind of how I think about it right now.
Right. A very closely related question came from Julian. Maybe you've already answered it. That could you imagine that this would lead to a new kind of a standard pre-trained model for vision tasks that is going to make the current vision models completely obsolete, and this would be like this would replace all of vision or something? Maybe you think that there's a good possibility there.
Yeah, my vision background is not my strength, but I think in many ways we're chasing the vision community in the sense that they were on this pre-training and sort of uniform architecture trend way before us. Maybe they have better ways of getting supervision, so maybe there's a little bit of a trade-off there in terms of exactly what kind of supervision. The self-supervision maybe came a little bit later. But the two fields are kind of dancing around each other, and I don't think it's like NLP is going to come and replace what they're doing, but I think this kind of mutual back and forth of exchange of ideas is very healthy and actually very much happening, and that's been a big part of the motivation of a lot of this work. And I think BERT and transformers and so forth have had very strong influence back to the models that are going on in computer vision too.
Right. One question that comes from Howie Young. How would you implement these things on edge? Because clearly there may be situations where you want to put this on smaller devices, and it looks like these models are such huge models that it will be practically impossible without the use of cloud communication.
Yeah, it's a wonderful question. And there's been some really great work on that lately. And so, I think roughly one way to think about it is over here in this part of the space, these models that are getting up to hundreds of millions of parameters can be compressed and distilled, and really interesting things you can do to get them down to be a reasonable size. And so I think there is potential, and I think that there's a whole community working on it, and they're slowly growing the space of models you can do. And another thing that I probably should have had a slide on is that efficiency is an active research area, and people are looking at conditional compute. They're looking at models that will fit better on smaller devices, and so as this trend up here, actually even this G-shard model here is a conditional model, but some of these other are dense models. We're sort of topping out. I mean, maybe there'll be another order of magnitude or something, but pretty soon, when you get up to hundreds of thousands of GPU days to train a model, it's just that we're going to hit a wall at some point. I don't know exactly when it's going to be, but it's not too far in the distant future. And then the whole game is going to be about efficiency. Now, that efficiency will also drive the next generation of bigger models, but it will also drive ever bigger models that can fit in smaller profiles. And I think it's a pretty exciting direction.
Thanks. So one question comes from Telenbu, and this is something that a version of that is in my mind also. So I'll share both questions. So Telen says, it seems like how language models are all currently doing is aiming for a universal language repository rather than being a good learner. So while there are some recent interests in meta few short learning, language learning, the base model is, however, still trained from a very, very large corpus where we as humans probably cannot even comprehend a lot of those knowledge in that corpora. On this account, what is your opinion towards small-scale learning, but growing it via methods such as continual or never-ending learning and or ablation research on probing, if language models are all really need that much amount of data? And my closely related question comes from the way child learns, the way you and I learn language. I mean, we don't just start learning from such a large amount of written text. Of course, we learn from interaction, and there is that natural difference. But even then, we have checks and balances at different points at every step of the way, and we learn language slowly. And the whole psycholinguistics is a very different way of looking at language learning, and the current pre-trained language models are an extreme far away step against it. So, what are your thoughts on these issues, both these issues?
Yeah, I think these are really great questions that get at the heart of the field. And also, I think our opportunities for great research, places where you could have impact without necessarily having so much compute, which would be really great. So I think in many ways, the reason we need so much text is because the models are so generic. They're such, a general hammer that they can sort of, and this isn't really true, but conceptually they can kind of learn anything. And so they need tons of data to latch onto the right dependencies, right? They're really, really data hungry. And so I think it'd just be really wonderful to focus on models that have a stronger bias, that can wring more from limited amounts of data. And in particular that, have, if you're motivated by intelligence, have, stronger priors like, say, a child language learner, or somehow maybe they're already grounded, they already have a model of the world, and now they just have to map that model of the world onto the language. I mean, that would be the ultimate dream. And in many ways, what we're doing here is just like running on an engineering trend. Of course, there's a lot of cleverness, but a big thing that's going on here is really hard engineering at scale too. And so I think flipping on that over and trying to think about better forms of supervision and ways of kind of bringing information in. I mean, I don't know how to build such models. And so, we kind of know how to build these models. And so, but that's good. That's a research opportunity. That's something we should all be thinking about.
Right, indeed. I do want to also check with you on the issues of factuality and common sense. Even in your example, you showed an example where the language looked beautiful, but it was factually incorrect. In your case, of course, it was subtly incorrect, and one had to read it carefully to figure out that, oh, this is actually wrong. But there have been more egregious errors that have come in every time. In fact, just today, in AAI, we also saw a paper where people were comparing comparisons, and if you give the model was not able to figure out whether because of the comparison dimension, what is the right comparative item to a given question, for example. And there are many such probing tasks that people have found, and the language models have not really succeeded very much. So where do you think is the issue? Is it because the models are being essentially glorified memorizers of text, and so they are not really getting to the core of what needs to be done? Or, how do we proceed? How do we move forward in being more factual about it and more,
It's just an excellent question. And I don't know the answer other than to say, like, it's pretty clear that these models are good at kind of interpolating based on the data. and maybe some limited extrapolation if you think about it in the classic machine learning sense. But I don't know that we've measured that well enough. I'm glad to see papers like that coming out. I think we're making slow progress in the birdology surveys and stuff. And I'm not saying there isn't work. There is definitely progress, but it's a really complicated thing, and it's hard to get into all the details. And so I think it's a reasonable hypothesis that what's going on is that you're just kind of compressing the data into the model parameters. And that, when you've compressed that much data into those parameters, you're able to find associations and do a bit of clustering and a bit of extra reduction, but you're not moving too far from the original data distribution. Turns out to be super useful for a lot of the benchmarks we have. And I tried to say at some point, like, we actually need better benchmarks. Like, we need to understand, how much progress we've actually made. So these sort of superhuman numbers are beautiful and, have real impact for industry and other places. But maybe those problems weren't actually as hard as we thought they were. And maybe we need to focus on some of these harder problems and more carefully measure what's going on. Things like common sense and so forth.
Right. Okay. There is one quick question on something. I mean, it's a more technical question. The question is by Rohangi. He says, do you know of any analysis of the convex polytopes spanned by context embedding vectors and the relationship of its metric geometry to the performance in various supervised tasks? A little bit more mathematical question.
Yeah, I don't know the full details there. I think that let's think about this. I think, well, it would be fun to poke around. I don't know of a whole lot of I know it exists in the word embedding space, but in the contextual word embedding space, I don't know as much formal work yet at understanding the sort of mathematical properties of these functions. And I think that's just kind of natural because the experimental side of the field is really pushing ahead faster than the theoretical side, which often happens in deep learning. I think if you go and look at things like learning word embeddings that are non-contextual, that are just on a token level, there's been some really beautiful math and really nice analysis and better understanding of what's going on. And I wouldn't be surprised if some of that starts coming up for the contextual case over time, but I suspect it's also much, much harder to analyze. Not being as much on the formal side myself, I sort of, it seems like that almost certainly be true. So it'll be interesting to see that trade-off.
Okay. And last but not the least, I'll ask you a question that I personally care a lot about. So as the trend has evolved in the last couple of years, because of these massively pre-trained language models and so on and so forth, a lot of research has actually moved from academia to industry research centers, where there is a huge amount of compute and huge amount of resources more easily available. And that has left the typical academicians like me in a little bit of a lurch, because so do you have any thoughts on how we who don't have access to industry scale resources, what is the kind of research questions, or what is the kind of research methodology or strategy we could follow to be more successful in NLP?
Yeah, and I live a dual life too, and so I have plenty of projects that are not running on supercomputers. So I totally believe that this is possible, and that there's really, really great work to be done, at all different compute budgets. I think that there's no one single answer. I think there's a potpourri of like exciting directions here. I do get this question fairly often these days. So I think an important part is asking the right questions. And so thinking about tasks and thinking about careful measurement is just really, really crucial. Especially if you have a lot of compute, you often just keep cranking away on the same task because you know how to do it. But we need to step back and make sure we're asking the right problems. I think there's a growing field looking at kind of the ethics of all this research and the social impacts. And I think, that's wonderful, and we should do a lot more of that. And then, we talked about this earlier, but I'll bring it back again, research and efficiency. So, I don't think that the only way to make a contribution is to have the very vast number on a task or to have the very biggest model. I mean, that's just silly. And so we need to really normalize the idea that something that is doing an interesting thing or that is performing really well for a fixed compute budget, those are major breakthroughs. Those are really important and they really matter. And we need to sort of reward them more, encourage more of that.
Great, thank you. Looks like there's still hope for people like us, especially if we focus on green AI as opposed to working on number chasing. So Thank you very much, Luke. A really enjoyable talk, really a broad overview, and also some cool, exciting recent stuff from you. Great hearing you.
Thanks for having me.
So that ends the plenary session for today. And of course, the next step is the poster session. And you already know where to go. We have to go to the Gather website to start the poster session. And this would be on for the next almost 1 hour, 50 minutes. So enjoy all the posters. There are two things I learned looking at the posters in previous sessions, which I thought I would share with you. First, when you reach a particular poster, you have to click X. And once you press X, you get to the poster for that paper. So that I think that would be useful information for you. And moreover, the 1-minute advertisement videos for the papers, they are available per cluster at the video booth just below all the papers in the Gather stream. So there is a separate section. There is a TV kind of an image there. You go there and you press X, and now you have ability to look at the 1-minute videos for the 8 papers in that particular cluster. I think that would be useful information before you decide which authors you want to talk to and so on. So enjoy the poster session and have a great rest of the conference. Thank you.